Hello everyone, welcome to the class once again. So our last class we were discussing about pressure. We learned about how pressure in a fluid is related with its height. We saw that it doesn't matter whatever the volume of the liquid you have contained in a vessel, the pressure at the surface will only depend upon the height of the liquid column. It will not depend upon the volume of the liquid column contained in the vessel. In today's class, we'll go ahead and we'll proceed from where we have left in the last class, and we'll start with practical application of pressure concept that we have learned. So if you are very well aware about the knowledge of pressure, you'll be very much easily understanding all this practical application of pressure knowledge. Practical application of the knowledge of concepts that we have learned. Now see, let's try to give a rationale to all the things that we observe in our day-to-day life. I believe that you all must be using boat pins. Safety pins you will be using. You must have seen that all those pins are pointed at one of its ends. Why is that? So first one, you must be finding that pins and nails are pointed. Now in our house also, we use nails which are pointed at one of its end. Now when we use pointed pins and nails, it will be very easy for us to use them. Now what happens as these edges are pointed, so as we apply a force, it will exert, for the same force, it will exert more pressure on the wall. Because we know that pressure equals to force upon area. Area is reduced, pressure will be more. So more pressure is exerted on the wall, and hence it easily presses into the wall. This is what the reason why the nails and pins are pointed. Second thing, just I'm discussing some general points about the application of pressure knowledge, which all you must be observing in your day-to-day life. See, whenever you walk on a ground filled with pebbles, it is very painful to walk on such ground. So it's painful to walk on a ground filled with pebbles. Painful to walk on ground filled with pebbles. Why is that so? See, our body has got weight. Our body has got weight. It will exert a force on the surface on which you are walking. Now, we know that from Newton's third law, the surface will also exert some force, same force on us. Since the surface area of the pebbles is very low, it's very small, hence it will exert more pressure on our feet, and we will feel a very pinching effect. So as the surface of the pebbles is very small, these pebbles are very small, and hence they exert more pressure on our feet. Their surface area is small. So you can reason out all these things. Surface area is small, hence more pressure. So that's why you feel that pain in your feet. Next thing, you must have traveled with railways. Using Indian Railways, you must have traveled. Have you ever observed the tracks? Those are laid upon white sleepers. That is, railway tracks are laid on white slippers. Railway tracks, they are laid on white sleepers. Why is that so? Let's try to give a reason for this observation. You know, railway, the trains are very heavy. As they move, their weight has to be balanced on the tracks. Now, as the weight is quite more, and the same force is applied, the force due to the weight of the rail will be applied on the surface. Now, to decrease the pressure on the surface, we are increasing the surface area. So that the surface doesn't go down, we are increasing surface area, because we know that pressure is equal to force upon area. So as you increase the area, the pressure is going to decrease, and hence the surface will not go down. It will remove still at its own position. It will not go down to a large extent. So that's why we are increasing the surface area by using white sleepers to lay the tracks of the railways. Easy observation. Easy to understand this observation. Some more observations, you must have seen that If you want to walk on sand, place white bar on it. And you must have also observed that when camels walk on sand, they have got a broad feet. Why is that so? Camels have broad feet. Why is that so? Camels have broad feet, and you can also, we have to lay broad planks to walk on sand. We have to lay broad planks to walk on sand. You know, because sand will move inside. Because as you walk on sand, your feet will go inside. So to save yourself and to have a safe walking, if you increase the surface area, your feet will remain still at the same position, it will not move inside, because as you increase surface area, the pressure exerted on the sand surface will be reduced to a larger extent. Now camels have broad feet because camels' weight, they have to walk through sand. If their feet is broad, the pressure they're going to exert on the sand, that will be reduced to a larger extent. Hence, by God's gift, they have got a broader feet. As God knew that they are going to walk on sand, so God has to make them to adapt itself to walk on sand. So these were some practical applications which I thought that at this point you should all know. What are the practical application of the knowledge of pressure? Next thing that we should know. I told you about the pressure in a fluid, and that depends upon the height. This same thing, there's a concept called Pascal's law given by Blaise Pascal, and he said that when pressure in a liquid is changed at one particular point, the change will be observed at every other point within the fluid. And before writing the definition, let me give you an observation. What do you do? Take a hollow ball. Take a hollow ball, and then what do you do? Prick some holes within that hollow ball. What do you do? Take a hollow ball, okay? Then you try to make some holes within this hollow ball. It's a small ball. I've shown it with some large area, large volume. It's a hollow ball. Now what do you do? Make a wider hole somewhere. If you make a wider hole somewhere and fill it with water. Fill it with water so that it is completely filled. Now what you do? You press your finger the wide hole, which I try to cover the wide hole, and let the water come out of all this opening. Let the water come out of all this opening. You will find that when they hit the ground, we are taking that the ball is small, you will find that when they hit the ground, they all are following with the same range on ground. That is what has been done. You are trying, after closing the finger, you are squeezing the ball. When you squeeze the ball, you are changing the pressure at the point where you are exerting the force. The same change in pressure is imparted at every point of the hollow sphere, at every point of the ball, and same change in pressure is observed, and hence they are following with the same range at every point. So first of all, let me write the definition and let me explain more nicely to you all the Pascal's law. It says that if pressure is varied at a particular position in a fluid, if pressure is changed at a particular, or at any position, not particular, at any position, or at any point in a fluid, the same change is observed at every point. The same change is observed at every point within the fluid. The same change is observed at every point of the fluid. What do we mean by this? The same change is observed at every point of the fluid. That means if you change the pressure at one particular point, the same change will be observed at every other point. To understand this, let me draw a diagram so that I can let you all understand this concept, Pascal's law. You should remember, if you're changing the pressure at one particular point, the same change in pressure will be observed at every particular point. First of all, I'll give a very simple demonstration. Let's take a vessel. Let's take a vessel given in this way. Let's say we are filling the vessel with some liquid. I have filled it with a fluid here, generally liquid we are talking about. Now, at any point, if we try to change the pressure, that is, let's say this has a piston over here. If we try to exert a pressure by forcing this piston inward, then let this point be A, this point be B, this point be C, this point be D. Initially all are at static condition. If you exert a pressure on the piston so that it can come inside, then this excess pressure with which you have inserted the piston inside, the same excess pressure will appear here. The same excess pressure will appear at A, will appear at B, will appear at C, will appear at D also, same excess pressure. This is what you are going to observe. This is what the Pascal's law says, that change the pressure at any point, you're gonna experience the same change at every point. One more demonstration I would like to give you to understand this Pascal's law. Suppose I am going to draw a figure showing a vessel in this way. Hope you are understanding that I am trying to show you all a container. Let's say this is A, this point is B, this is C. Now here we have 3 pistons connected at each of the openings that I have drawn. I have made 3 openings. Let me fill this entire container with a fluid. Hope that you are getting that I am filling it with a fluid as shown here. Now you see, let's say the surface area of the piston in 3 cases is different. Let's say here the surface area is given as x, here it is 2x, here it is x by 2. This is what we have done. Now let's say you have applied a force F through this piston, through this part of the piston. You have applied a force F at point A. Now what will be the force experienced by this piston and by this piston? Because as you are trying to force it in this direction, it's quite obvious for us that this piston and this piston will try to release itself, they will try to move up. To keep the piston, now with what force they are going to experience, let's try to understand. Pascal law says that the pressure change at any point within a liquid the same change will be observed at every point. So here the pressure change that you are giving, the change in pressure at this point that you are giving, that is equal to F by X. The same change should be observed here. So let us say the force experienced by this at this point is given as F1 and the force experienced at this point is given as F2. Pressure change will be same. So let's say it's F1. So pressure at this piston will be P equals to F1 by 2x. So I'm writing at this position, you must be having pressure P equals to F1 by 2x. Pressure change will be same. It will be F by x. So I'm writing this F by x and this is F1 by 2x. it's quite obvious for us to get that F1 will be equal to twice of F1 will be equal to twice of F. You can see that F1 will be equal to twice of F. That means twice the force you are experiencing here because of changing the area, because Pascal says that, Pascal law states that if you change the pressure at one point, the same change will be observed at every point of the fluid. Now let's go ahead with this part. The same change will be observed here also. So here you see, let's say the force is F2. So we know that pressure at point 2, at C we are talking about, at C, pressure will be equal to F2 by phase area x by 2. So this will be given as this, and this change in pressure is nothing but F by x. So this comes out to be, this 2 will go up, so F2 will come out to be F by x. This is what we know. F2 will come out to be F by x, that is the force experienced on this piston will be just half of the force that was exerted here. Easy thing, Pascal law, I now believe that you must have understood about Pascal's law. When you vary pressure at one point, the same change in pressure will be seen at every other point within a fluid. Let's go ahead. Now, why we have learned this, are there any practical application of Pascal law? Just now this demonstration only, we have, with this demonstration we can understand an application of Pascal law. This demonstration that I gave you, we saw that you are exerting a force F. You obtained twice of force F in one of the situation, in one piston, and just half of the force with the other piston. Now see here, the first application is based upon this concept only, and let's go through the first application of Pascal law. Application of Pascal's law. First one is hydraulic lift. Hydraulic lift is the first application. I believe that you all must have taken your car to a service station. If not your car, you must have seen at service station, when a car is made to be lifted, it is brought at a certain platform, and then the car is being lifted with the help of a lift. Let me tell you that lift works on a principle of hydraulic lift, and this hydraulic lift works due to the application of Pascal law. That is, we can give a rationale for the working of the lift by understanding the Pascal's law by using Pascal law. Hydraulic lift. Now see in hydraulic lift what is the case. We have one narrow tube, and then this narrow tube is connected with a wider tube. This is the way in which these two tubes are connected. This is the situation. Let's say the face area, the surface area, and now before going with surface area, let me show you that we have two pistons here. This is piston at point A, and here we have one more actually plank here at which you can put a load. Let me put a car over here. Hope you are getting that a car is placed here. Now you see here the weight of the car will be very much high. It's quite larger in magnitude, the weight of the car. How to lift it with the help of hydraulic lift? Suppose you apply a force F here. You apply a force F here, and let's say you are obtaining a force F dash over here by applying a force F here. What will happen when you apply a force F? This piston will go inside into this, as this liquid is contained here. This liquid will try to exert a force on this piston, and hence this is going to move up. But A car is generally, let's say its weight is around, let's say 2 tons, around 2000 kg, let's say. How are you going to lift it? By applying, you cannot apply such large magnitude force. So how this arrangement will help us? Let's say the face area at this part is given as small a, and here the face area is given as b, small b. Remember, I am talking about this area of cross section of the piston. Now say here Pascal law says that change in pressure at one point, the same change will be observed at the other point. We have exerted an excess pressure that is given as F by A. Here, if the force is F dash, the excess pressure that you should obtain, that should be equal to F dash by surface area B. Change in pressure has to be same. So shall we equate F by A is equal to F dash by B, and let me write here in this way: pressure P is equal to pressure P here. Change in pressure will be same in both the cases. We know that. Now here we have applied on a small area a force F and pressure is equal to F by A. And here we have applied a pressure P and we have shown that force acting on this point is F dash. We want to see what is the value of this F dash. And before that, I need to use more part of the board. What you do, take note till here. I will start explaining from here the other part of the board. Okay, you must have seen that I told you the change in pressure will be same here also and here also. Now I'll be going to some right part. So see here, pressure change is same. So we can write F by A is equal to F dash by B. So we can write that F dash is equal to F into B by A. This is what we are going to observe, F into B by A. You can see that the surface area B is greater than the surface area A. The area of cross section of A is smaller than the area of cross section of B. So hence we can write that F dash will be greater than F. So if you keep the cross sectional area in such a way that the ratio, how many times you want the magnitude of the force to be more, you keep the area of cross section in that ratio, you will get multiple times of force as the output compared to the input force that you are applying. So you must be thinking that by applying a smaller magnitude force, you are obtaining a larger magnitude force. Is it invalidating or is it invalid with the law of conservation of energy? No, you are not breaking the law of conservation of energy. Still, the work done by you will be equal to the work done by on lifting the load. Because you can think in the same thing in this way, you will go more depth down compared to the height that will be raised. Height raised will be lesser here compared to the height that you are going down. So you have to do that much amount. The work done, if you try to obtain, what is the work done by you? That will be F into your height, and the same thing if you go ahead with this F dash into your small height, both work done will be same. So you're not breaking the law of conservation of energy, although you are getting more force output, but still the work done is same in both the cases. As much amount of work you do, that much amount of work you are going to obtain as the output. So this was the first application of Pascal law, in which we have got that you can produce more magnitude of force by applying a lesser magnitude of force, and this is used in case of hydraulic lift. The second application of Pascal law is the hydraulic brakes. See, I have a figure here. I want to show you all this figure. See this figure, this is a hydraulic brake arrangement. You see, this is the brake pad. When you generally move in your car or in your bike, you apply the brakes by pressing the brake pad. There is some lever arrangement. Then we have a cylinder over here. We have a cylinder, there is a piston over here. This cylinder is the master cylinder. Okay. Now there's a piston over here. When you press it, the lever arrangement will make the liquid to move inside. And these pipes are connected to strong pipes through which liquid is flowing. Now this liquid is again here. What happens? You are applying a lesser magnitude force, but due to the difference in area of cross section, this is a more area of cross section is here. So what happens? It gets lifted. It gets lifted. By applying less force, you will be exerting more force over here. Just now I told you in the case of hydraulic lift, in the same way the principle of working is the same in the case of hydraulic brake also. More force will be acting here, so this part is going to move up. You can see this inner part is going to move up. Now what happened? This is a brake shoe. Then this is going to exert a force on the rim of the wheel, and that's why the wheel is going to stop. It is not going to turn. This pipe is leading to other wheels. Now what happens? As you release the pressure on this brake pad, what happens? There is a spring arrangement here. It will bring back the initial state of this part of the brake shoe. Then what happens? It's going to insert the piston inside, and hence it will again expand and brake will reach to its initial position. This is the working of hydraulic brake. In the same way, because what you're doing, you're applying a less force and you have exerted a pressure on this piston. Since change in pressure will remain same, but you have increased the area of cross section over here. So just now I told you, if you increase the area of cross section, you are going to obtain more force, and hence you will see that more force will be exerted here, and this is going to move up, and your wheel is going to stop in this case easily by applying a low magnitude of force. So this is how the hydraulic brake works. This is how the hydraulic lift works. Let us go ahead from here and let's learn about the next concept, that is atmospheric pressure. So we were talking about pressure in a fluid. We were confining ourselves to liquid. Now let's go to atmospheric pressure. We have a wonderful large atmosphere all over us, all above us. We are all surrounded by a very large atmosphere all over us. Now, let me tell you the air which is around us that is exerting pressure on us. And we do not feel that pressure. Why is that so? Because blood is running in our veins, in every part of our body. So blood has its own pressure. And that's why when blood has its own pressure, it will exert a force outward of the skin, and the air is pressing inside or on our body. So hence both pressure actually cancel out the net force on our body, and we don't feel that large amount of pressure. How more you can understand that air above us is exerting pressure on us? What you do, have you ever observed, if you take a water bottle, what you do, you must have seen this thing normally. Take a water bottle, place some warm water over it, which is vapors are coming out of the water. Place some warm water within it, such that vapors are coming out of it. You close the tap. What will happen? We can see that the entire part will be having vapor above the surface of water. Now cool it, let it cool. When it cools down, this vapor will condense, it will form droplets, and it will reach again to the surface of water when the vapor condenses. That means there will be a vacuum space that will be formed over the surface of water. Vacuum will be formed over the surface of water. Now what happens? Air from all around, it's going to exert pressure from everywhere. It's going to exert pressure from everywhere. As this part is vacuum, the bottle is going to get crushed, because initially the entire part was filled with air. So this part was also exerting pressure outside, and the pressure due to the atmospheric pressure was there. So hence it remained in equilibrium. But as this part became vacuum, there was no pressure to counter this external pressure, and hence the bottle gets crushed. One more demonstration. Let me tell you a story about the idea of atmospheric pressure. Now in 1654, years ago, centuries ago, Otto van Guericke, you can just confirm this spelling, this has got complicated name, Otto van Guericke. This man, to have an idea about the atmospheric pressure, what he did, he took two hollow spheres, and actually they were semi-hollow spheres. It were just half of a complete sphere. If you take two hollow semi-spheres, Otto van took those spheres and actually joined them in this way. What he did, he took two hollow spheres and he joined these hollow spheres by the help of a leather arrangement, actually washer arrangement, so that no air can pump in, no air can come in. Now with the help of a motor pump, with the help of some arrangement, he withdraw all the air from inside of this arrangement. Took two hollow spheres, you can imagine two hollow spheres, and he joined them in such a way that no air can enter the hollow sphere, and he pumped out all the air from inside of the hollow sphere. Now what happened, he was trying to let them move away. He was trying to remove them separately. He was trying to separate them each other, but it was very difficult to separate it. And it is said that he connected these spheres from two sides, and he joined ropes, and these ropes were connected to horses. These ropes were connected to horses such that 10 horses were pulling from each side. If I try to draw, it will be very difficult for me to show you a horse who is trying to actually pull it, but then too it was finding it difficult. If it is tied here, then too it was finding difficult to separate these two spheres. This is what the actual story went. This was the thing that happened. This is connected with this horse. Still they were unable to break it off, to separate them. Why it was so? There was no air inside. Inside it's completely vacuum. There was no air inside. Why it was so much difficult for it to be separated? Let me tell you, because air is exerting pressure on it. Air is exerting pressure on it from every corner, from every side. If you try to understand what a large amount of force the air pressure can apply on a body, try to understand. See, if you try to find out the resultant of the forces acting due to this on this part of the semi-hollow sphere or hollow semisphere, you will be having a net force due to air along this direction and a net force along this direction due to the other part of the hollow sphere. This force was of such a strong magnitude, it was such a high magnitude that it was very difficult for them to be separated. So we got an idea that yes, air pressure can exert a very large amount of force. That means air pressure is quite enormous. It's quite large in magnitude. With all these demonstrations, people came to know. Now, how to evaluate the atmospheric pressure? First of all, let me give you the value of atmospheric pressure. Atmospheric pressure in terms of SI unit, we will be generally using this atmospheric to denote atmospheric pressure as P naught. It is given as 1.013 into 10 to power 5 Newton per square meter or Pascal. And this much amount of pressure is only known as 1 atm, or generally what we are going to do, 1 atm, that is 1 atmospheric pressure, we are going to take approximately the value as 10 to power 5 Pascal. This is the value of 1 atmospheric pressure, that is equal to 10 to power 5 Pascal. So we have obtained this much. Now, how to measure this large amount of atmospheric pressure? It was actually the method was given by Torricelli to find out the value of atmospheric pressure. What he did, he took a mercury container, he took a tube, and he filled the tube with mercury. He took a very long tube, 1 meter long tube. He filled the tube with mercury, and then he inverted the tube over the vessel in which mercury was initially kept. So this is the Torricelli arrangement to measure the pressure, atmospheric pressure. Suppose this is a vessel in which you have filled entirely vessel with mercury, and he took a tube, 1 meter long tube, he poured mercury inside it, and then he closed the top end with his thumb. He inverted such that no air can move inside, and this is the way in which he inverted. He found out that the mercury level came down because it was 1 meter long tube, but it came down here and this much part was left vacant. This is the situation. That we have arrived at after his arrangement. This height, he saw that this height is equal to 76 centimeter. Now, why this height is 76 centimeter? We know that pressure at every level will be same. So pressure at this level, because it's open to atmosphere, I am talking about 3 levels, A, B is this, and C. Pressure at the 3 levels will be equal. Pressure at A is equal to pressure at B is equal to pressure at C, and this is equal to atmospheric pressure P naught. The pressure at point B will be due to the height of the mercury column, and this will be equal to, pressure at B will be equal to height of mercury, density of mercury. So I am writing rho Hg because it's mercury, rho H, rho GH we have mentioned. So atmospheric pressure can be given as P naught density of mercury into G into H, that is 76 centimeter. You have to mention H here as 76 centimeter. Rho of mercury is 13.6 into 10 to power 3 kg per cubic meter. Acceleration due to gravity is 10 and height is 0.76 meter. I will give you this as an assignment for you all to find out the value of atmospheric pressure from this data. Try to find out. I will discuss with you all the value of this in the next class also, and I will discuss more points about this Torricelli arrangement, what is this arrangement called, in the next class. This arrangement actually is helping us to understand the value of atmospheric pressure. We will use some more liquids to find out what will be the height column when you are going to measure the value of atmospheric pressure, and that we will discuss in the next class. Today's class we talked about Pascal's law, some application of pressure knowledge, and then how we saw that how the knowledge of pressure can actually lead us to simplifying things in our day-to-day life. Pascal's law we constructed using the help of Pascal's law as hydraulic brakes and hydraulic lift. In the next class, we'll be talking about more about pressure, more about atmospheric pressure. We'll talk more about it, more about the arrangement here in the next class. Till the time, do take good care of yourself and do start practicing problems based upon the simple concepts. Do revise and wish you all the very best. Thank you everyone.